Okay, I would like to start by thanking everybody who's attending this webinar. And yeah, good morning, good afternoon, or good evening, depending on which part of the world you're attending from. This is Niccolo Giannetti, and I am very glad to have the opportunity to present the results that we have published in this report within the subtask 1 about testing methodology and performance rating standards, together with all the other members of this group. So I am presenting on behalf of the whole group. So yes, so this is the first chapter of this report, and I think it has a particular importance for supporting the result that are presented by other group as well. So today I structured my presentation according to these 5 main parts. First, I will try to describe the background, the motivation that stimulated this activity, and the scope that we recognize as the main objective of this work. As also Professor Takao and Professor Alberto already mentioned, this part will focus on 2 main categories of testing standards. So we categorized the past and ongoing work on this subject in 2 main categories. Category A, where we review presently adopted testing methodologies and performance rating standards. And then category B, which will be part 4, which reviews a new proposal for performance tests that are conducted when the tested unit is operated with the same control as it would operate in a building. For this subsection, we have decided to start and represent the state of the art of these ongoing activities with the contribution of 4 main leading groups that are working on the developing of this new test method and rating standards. Of course, the activity is still ongoing and reviewing other contribution, and we will also trying to harmonize the findings and try to converge towards a more defined and single method for future testing of heat pump and air conditioners. So finally, I'll try to conclude with the main findings and maybe describe what are the main perspective within this activity. So let me start with the background that defines our motivation. So the technology that we are targeting, as you have understood, is that of a heat pump. So heat pumping intended as both for cooling and heating. So both heat pumps, hydronic or air-to-air or other type of heat pump ground source, and air-to-air, which includes also air conditioners. So we know that this technology has been extensively installed worldwide. So we can observe maybe numbers that lead up to billions of units already installed worldwide in the case of air conditioners. And these are operating systems that interact with building features, normally operate with inverter technology, so with a control that is responding dynamically to given loads, then interacts with variable lifestyle or comfort standards, but also with different climates worldwide. So we know that the hardware performance of these devices, of these systems, are relatively well represented by current standards. So we have current standards that can give us a clear number about how efficient is this heat pump when tested according to these performance rating standards. But for some reason that we will be investigated and describing later, even though we have such an extensive application of this technology, we do not have a clear knowledge about their operational performance. So how these systems actually operate in the field, and how efficiently they are operating when interacting with actual field environment and when operating with their own native control. So, okay. So I think we can first start describing how this system operate in a building. So in the case of an air conditioner, we can imagine how this unit interact with the indoor environment by its own native control, so the control system that is installed inside the unit and that senses through the thermostat variation of the indoor unit and try to operate the system to meet the set temperature that we control with our remote control, or that is controlled centrally by a central system. Most of the time, these systems do not operate in steady state operation, where cooling capacity, in the case of air conditioner, is perfectly balancing building load. But in practice, these two quantities might have an imbalance, and any imbalance results in a indoor condition variation, for example, temperature or humidity. And this variation, or the rate of this variation, is dependent not only on the magnitude of the imbalance, but also on the characteristics of the building, so the thermal inertia of the building. So how slowly or how fastly this temperature is changing in relation to this imbalance between capacity and load. So here is just to exemplify what I just said. So for example, we can imagine that if our air conditioner is installed in a room that have certain characteristics and is turned off, the room is subjected to external loads that gradually infiltrate inside the room in a summer operation. And we can imagine, starting from a given temperature, for example, 27 Celsius, how this temperature will be increasing gradually due to this additional heat coming from outside. The blue line just below the one I just described could represent the indoor state changing when the air conditioner is steadily providing half of the needed capacity. So if we're providing half of the needed capacity, this could be what we experience inside the room. This temperature variation will be increasing, but more slowly. Or if we're providing, the air conditioner is providing exactly the cooling capacity that is balancing the cooling load or heating load, then we would have a perfectly constant indoor temperature. During active control operation, we have that the control reacts to the sensor placed in the thermostat, and with modulation of control parameters such as the compressor speed or the valve opening for an air conditioner or a vapor compression heat pump, that adjust the operation in a way that cooling capacity is supplied in as precise as possible manner to maintain the indoor condition as close as possible to a set point. But minimal variation are required for the sensor to sense the indoor temperature variation, and correspondingly the control system responds with the modulation of the system operation. The orange line is maybe somewhat different case that might be representative of lower load, where we have that maybe the control in some condition is not able to meet this, is not able to adjust the compressor speed or control parameter to meet exactly or to move around the set point. And at a certain point, we'll have to switch off the compressor. And so we will have a system that might operate in a cycling on-off operation. So from this preliminary observation, we can clearly say that also for the fundamental characteristics of heat transfer, that heating and cooling technologies, such as heat pumps, not only depend on time, so have performance that are time dependent because of their internal control, They depend also on external parameters, but also on the interaction with the building features. So the main issue that we're targeting and recognizing for starting the activity of this group was that of a gap between product performance that are reported in catalog nowadays and building performance that might be observed in an actual building installation. So this gap could be is the result of somewhat inconsistent viewpoints between heat pump designers, air conditioner designers, and building owners or building designers. This led also to different technical approaches, but is also a result of inappropriate design, inappropriate control, and sizing or installation of the heat pump within the building. And as you can imagine, this can limit the potential of the heat pump technology as a key technology for decarbonizing the building sector and as an efficient integrated part of the building. So the scope of Annex 88, I think, can be summarized as mentioned previously by Alberto and Takao, as trying to provide a more harmonized viewpoint and also having transparent technological information transfer on heat pumps between both technical expert, building owners, but also policymakers. So to reach this scope, we recognize that main developments have to be obtained in these four main fields. So one is development of new testing procedures, then the development of accurate energy calculation method, then correspondingly developing design and commissioning guidelines that are efficiently leading to efficient operation. And then finally, having a way to monitor and to visualize the performance of this system once installed in the actual building. So have a feedback on the whole previous work that has been done. So testing procedures are the first step to be addressed in this path. And this chapter focuses on the activity that is ongoing and the activity that came before current research on testing procedures. So this part has three main scopes. It first starts by reviewing the recently adopted testing methodology and performance rating standards, so category A standards, to provide a clear picture of the state of the art in a current testing methodology. Then moves to the review of some examples, maybe the leading examples of new testing procedures that are being developed or have been developed for assessing the performance of heat pump and air conditioners when operated with the same control as operated in buildings. And these are category B standards. And then finally, consider how to use the results obtainable by this new testing methodology to push more effective design and control, and also maximize the performance of this technology in building. So just to be clear, again, this slide clearly states what are the difference between category A and category B standards. Category A standard or current standards are required tests that are conducted by utilizing some special kind of test control, so proprietary control, that force the system into a steady state operation during test that would not necessarily occur in the actual operation. So the actual control, so native control of the system is deactivated, and a special control is included to obtain this special condition. So when tested in this condition, these tests testing methodologies can provide values that are representative of maybe the equipment performance or hardware performance. But as the control system has been deactivated during this test, the results are not able to characterize the performance that is encountered in actual building. So on one hand, many people consider that this kind of approach is somehow necessary to have high accuracy and high reproducibility level of the results. However, with this report, we bring in some new opportunities for actually obtaining results that are as reliable, but not only representative of the hardware performance of the unit, but also of its operational performance. So during this test for category B, the system is always operated under the same control as operated in buildings. So there is no need for any addition or connection to special proprietary control during this test. Okay, and we have evidence already that this test can have comparable reproducibility level, accuracy, and definitely higher representativeness of the result when compared to category A standards. So starting with category A standards, we said that the system operates, in this case, in a forced steady state operation. So in this test, the capacity supplied by the indoor unit is kept constant by fixing the compressor speed during this test. And this on the right side is an example of the test result that we can obtain during this kind of test. On the left side, we have one example of equipment. So in this case, the air enthalpy testing facility with 2 psychrometric room. There are also balance type testing facilities. And yeah, this is generally a good example of a common type of equipment that is required for this test. In the report, category A standards are reviewed, and this is a simple list of the main standards that are referenced in the report. These includes international standards, European standards, American, and Japanese standards. And each of these voices is reviewed by focusing on what kind of system is targeted by the rating standard, what kind of test method, in which conditions the performance is assessed, what kind of control is needed during test, performance indices that are used, and the tolerance of measurement during the test. Below, I reported a simple example on some cases of result obtained according to these Japanese standards to just give an idea of what is the level required in the reproducibility of the result. So this is the result of an interlaboratory test. So 2 different facilities tested the same unit and obtained results that are consistent within 3% error, which is also a requirement of this test. Other requirement, I think AHRI 210 to 40 requires 6% error. This is just a reference to compare following results of category B standards. So category B standards or new testing methods that are being developed at present to overcome the limitation of previous standards need to focus on these additional points that are challenges, but also opportunities for more valuable information extracted by each test. So the unit should be set up in the same way as is installed in a building. So no proprietary control is needed. The thermostat is operated in the same way as it's operated in a building. And so this comes to point 2, where the unit is operated according to its native control and follows the response according to the temperature or humidity, in case there is a humidity sensor of its own thermostat. During this test, we should be able to capture efficiency losses that comes from the use of the inverter, so a variable speed technology. This is usually a technology that provides the possibility to operate efficiently in a broad spectrum of condition, so no fixed speed operation. But if the control is not properly designed, then we encounter also losses because of their inconsistencies. Then actually operating the system as once installed, as it's operating in a building, this provides opportunities to automate the test. So actually nothing needs to be changed once it's installed. Just the outdoor condition needs to be set, and then the system needs to be operated as it would be operated by its remote control in a building. So yes, I'll come to this point back later. Then should be able to capture the interaction of the system performance with the building thermal features, so the thermal inertia of a room where it's installed. And these automated tests and these tests operating the system as it would be operating in the field also prevent some, let's say, procedure that could artificially inflate the efficiency of the system during the test. So the main contributors to the development of these new testing methods and literature are reported here. Of course, these are not we're not claiming this to be conclusively or let's say comprehensive. There are other groups that we are in contact with, and we are open to get their contribution as well. So the four main contributions I will be presenting today come from Waseda University, CSA, Canadian Standard Association, Better Living and BRI in Japan, and BAM and Aachen University in Germany. So these, let's say, 5 groups, the last 2 are reported together. They have been working, cooperating since long time together, mainly focus on slightly different units and with similar approaches for the test. So Waseda focuses on air-to-air units, the same as CSA. BRI focuses on multi-split air-to-air units or VRF system, while BAM and Aachen University focus on hydronic heat pumps. So heat pumps with air or water source or ground source that deliver, so supply cooling and heating effect with a water circuit. Okay, let's start with Waseda's contribution. So Waseda started its activity on this subject in 2014 with a national project that was aimed at developing a new testing method that was able to capture reproducibly the control response of variable speed air conditioners. So we have discussed before how the air conditioner operates in an actual building and how it interacts with the surrounding building features. So there are some challenges that need to be addressed to have results that are reproducible across different facilities. So this is done with this method that we called emulator type load-based test that uses the same testing equipment as current standard, so a simple air enthalpy testing facility, and combine this with a software where we call the room emulator, to which we delegate numerically the task to calculate in real time the evolution of the indoor space condition according to the cooling or heating effects applied in real time and measured in real time by the unit that is tested in the testing facility. So the communication between hardware and software part is possible through these 2 main devices that are the condition generator or reconditioning unit of each psychrometric room, and the measuring chamber where we can obtain real-time measurement of cooling and heating effect. As a first part of this activity, we focus on making sure that the measured measuring procedure is reliable and reproducible across different facilities. So beside accuracy of the sensor, we had to look into all the sources of thermal and transport delay that occur inside the testing facility, and we address them with by observing if they're negligible, comparing to the the time constant of the operation of the system, like in the case of the calculation time of the room emulator or the delay coming from the sensor themselves. Then the trackability of the air conditioner, the air condition at the supply port. So volumetric flow rate of the air needs to be measured for the cooling capacity, as well as temperature and humidity measured after collecting the air flux from the indoor unit and measuring its value. Yeah, this was the delay of this was bypassed by using a thermal grid of thermocouples calibrated to the PT sensor to maintain accuracy and bypassing the delay of the chamber itself. Okay, other delay could come from the condition generator itself, and we developed a feed-forward compensation method that models the delay, and with a simple linear model, reverse the calculation to minimize this delay and offsets during dynamic operation. This is not necessary to be used, is only required whenever the reconditioning unit has substantial delay. This is an example of the result that we can obtain in corresponding condition. So fixed compressor speed result and emulator type load-based test results. The COP is substantially different, over 25% difference in low load conditions, such as this one, so 25% load. Then the emulator, so the software side, gives us the freedom to simulate any building feature, in this case, different building size with different building inertia. So this is a virtual building, but the system obviously responds with different dynamics to the same load, but with different thermal inertia of the indoor space, leading to also different COP. And reproducibility studies have been conducted within different facilities, and we could observe that addressing all these sources of thermal delay and transport delay, results could be accurate and reproducible within 3%. So then very quickly on the other methods. So we have CSA's activity that also started around 2015 and focus on air-to-air unit tested with load-based test with a method that is used to calculate seasonal COP values for different climates, for example, those of North America. So their activity has been published in 2 times. First technical review in 2019, already a draft of a rating standard procedure, and the most recent one, SPE 0723 in 2023. Sorry, this one. That is a published and available standard that can be used for conducting tests, which include both test procedure and also performance rating calculation. In their result, they brought in a very valuable contribution in confirming the representativeness of this testing method, emulator type load-based test. So confirming that the result obtained with this method come closer to those measured in the field when compared to the corresponding unit measured according to AHRI 2010-2040. Then Better Living and BRI focus on multi-split VRF system. So they address the challenge of having multiple indoor units with unbalanced load, and also confirming result with the result confirming that it's needed to, that deviations are obvious with respect to the catalog values. Then, as I mentioned before, the BAM, the Federal Institute for Material and Research and Testing in Germany, review current standards in Europe, EN 14511 and EN 14825 for hydronic heat pumps, and also adopted a method that is load-based test to test the unit when operated with its own built-in control or native control. Recently, they republished, revised the methodology with a new draft that introduces the virtual model of the building and the inertia coming from the pipelines of the hydraulic system. And results are being reported, confirming, enhance representativeness and enhance reproducibility of the result. And finally, Aachen University working on the hardware-in-the-loop approach. So the hardware-in-the-loop method is something that has been used largely in the development of electronic system, electronic appliances, or automotive industry. But in this case, it's applied to the the heat pump technology, hydronic heat pump technology, with a specific attention not only to the system, but also to the whole energy system around the heat pump itself. So in this case, the simulated part is not only the indoor space, but includes also condensing unit, storage unit, and the environment. And in this case, the approach does not require a constant outdoor temperature like in other standards, but test the system in a variable outdoor condition that could be representative of a day or the whole year. Okay, so coming to the conclusion, I would like to remark that testing methodology are a key step to develop effective minimum energy performance standards that could drive a reduction of the environmental impact of this technology. It's the basis for obtaining performance assessment, and with new method could be used to capture operational characteristics, verifying design efficiency and control efficiency. And accordingly, could stimulate the technology development, both in design, control, but also guide consumers to more effective choices, and also drive the development of more evidence-based policies. So the review of new testing methodologies could be summarized by these main findings. We know that load-based tests rely on the same equipment and instrumentation required by current standards, so does not require a substantial additional burden to the industry. At the moment, we could find that tests require slightly larger time than current fixed speed test, current standards, but this could be actually an opportunity, could be solved with more experience, and the fact that the system is operated in the same way as in a building could be an opportunity for making the test automatic. So using 24 hours without necessity of intermediate adjustment of the unit or the flow rate of the air. So making the test automatic and maybe also saving time in that perspective. And then since results are more representative and also have similar accuracy and reproducibility, this result provides additional value when compared to previous standards, and provide opportunities to harmonize and bring closer the activity of building designers and heat pump manufacturers. Yes, so yeah, with this, I would like to conclude my presentation, and thank you for your kind attention. Apologies if it was a little bit long.